Let's build on the previous video by doing another hypothesis test. For this video, we will be working in the right tail of the standard normal distribution. We will test the hypothesis that the mean of this population is equal to 90. We will start with a hypothetical sample of size 4, which means that the sampling distribution, according to the central limit theorem, has a mean of 90 and a standard deviation of 5. Let us further suppose that our sample of size 4 has a mean of 101 and is located here in the sampling distribution. For this test, we will require a level of significance of 0.01. Remember that the level of significance is the maximum probability we are willing to accept in making a type 1 error. That is, to reject a null hypothesis that is in fact true is a mistake, and we wish to make its probability very low. Our null hypothesis will be that the population mean is equal to 90, and the alternate hypothesis will be that the population mean is greater than 90. Because we decided that the alternate hypothesis is that the population mean is greater than 90, this will be a right tail test. The level of significance is a probability and is represented by an area in the right tail. The critical z-score, which has an area of 0.01 to its right, implies that the area to its left is 1 minus 0.01, or 0.99, which is the value we need to use the z-score table. Since we are working to the right of the mean, we will get our z-score from the positive z-score table. The closest we can get to 0.99 is 0.9901. The z-score with this area to its left is 2.33 and has an area to its right of 0.0099. For this example, 0.0099 is close enough to 0.01 to say that it is 0.01. We will store the critical z-score here. We now need to calculate the test z-score. Recall the equation to calculate it. It is the sample mean minus the population mean divided by the standard deviation of the population, which is divided by the square root of the sample size, and is equal to 2.20. We will store the test z-score here, and locate it here in the standard normal distribution. The p-value is the area to the right of the test z-score, which we will now determine. The area to the left of 2.20 is 0.9861, and the area to the right of 2.20 is 1 minus 0.9861, or 0.0139. The area we just found is the area to the right of the test z-score and is the p-value which we will store here, and that area is shown here. We can now conclude, because the p-value is greater than the level of significance, we will decide to not reject the null hypothesis. We are saying that this difference is not significant enough for us to conclude the population mean is greater than 90. Let's now see what would happen if the difference between the sample mean and the population mean were to become larger. As the difference between the sample mean and the population mean becomes larger, the test z-score becomes larger, and the area to the right of the test z-score, the p-value, becomes smaller. When the p-value is less than the level of significance, we are comfortable in rejecting the null hypothesis, in favor of the alternate hypothesis. This is the equivalent of saying the probability of making a type 1 error is less than the maximum value we would accept. Let's return to a sample mean of 101. The significance of the sample mean is also impacted by the sample size. Note what happens to the test z-score if the sample size is increased to 5. The recalculation of the test z-score results in a value of 2.460, which is greater than the critical z-score, and results in a p-value of 0.0070. So once again, the probability of making a type 1 error is less than the level of significance, meaning we will be comfortable in rejecting the null hypothesis, in favor of the alternate hypothesis.